Welcome to Teja Statistics. In previous class, we discussed about the notations and terminology in our stratified random sampling. Let's see the theorem number 1. Y bar of ST is an unbiased estimate of the population mean. That is y bar of dot dot. Y bar of n. Okay, expected value of y bar of ST is equals to y bar of n. Just proof, very simple proof. Since the sample in each of the stratum is a simple random sampling without replacement, we have expected value of y bar of ni is equals to capital Y bar of n. So in stratified random sampling, expected value of y bar of st is equals to 1 divided by capital N summation ni into. So expectation over here y bar of ni, then 1 by n into summation I runs from 1 to k, ni into y bar of ni. So both n values are gets cancelled, or we can have the formula of that. Then expected value of y bar of n, if you substitute it there, then it is a capital Y bar of n. Simply we have the notation and terminology in our case. Next, theorem number 2. Prove that variance of y bar of st is equals to 1 divided by capital N square of summation I runs from 1 to k ni into ni minus ni of si square divided by n. So we have the formula of p. In terms of p also we have. So what is pi value? Capital N divided by capital N. So this can be simplified like this. Next, since the simple sample in each stratum is a simple random sample without replacement, variance of y bar of ni is equals to 1 by small ni minus 1 divided by capital Ni of si square. So just we are adding the I values extras. So in a stratified random sampling, so variance of y bar of st formula, that is I runs from 1 to k, a p of I of variance of y bar of summation I runs from 1 to k pi into y bar of ni. So expectation and the variance also will be applied for the variable only y bar of ni. So variance of y bar of ni is equals to 1 by summation I runs from 1 to k pi square into 1 divided by ni minus 1 divided by ni of s square. Here s square is missing. Okay, what is substitute the value of pi value over here? That is ni square divided by n. If you put si square in the next step, that is ni square divided by n square, and this will become 1 by n square of summation I runs from 1 to k ni square of cross multiplication doing the LCM ni minus small ni divided by ni of si square divided by small ni. Then variance of y bar of st is equals to ni of ni minus ni of s square divided by ni. Hence proved. So thus we see that variance of y bar of st depends on si square value heterogeneity with some status. Okay, next coming to the another proof, that is allocation of sample size. Here in stratified random sampling, very important terminologies these are all. Allocation of sample size. In stratified random sampling, we observe that variance of y bar of st depends on ni. The sample size for ith stratum, which can be fixed at will. The allocation of the sample sizes for different status is done in the following two ways. First one, proportional allocation, and the optimal allocation. Now what is proportional allocation? Let's see. Allocation of ni's is the various status is called proportional allocation. If the sample proportion small ni divided by capital Ni is a constant for each stratum, ni divided by n, n1 divided by capital N1, small n2 divided by capital N2, and nk divided by capital Nk is equals to be the constant. Okay, here ni is directly proportional to the capital Ni. Thus, in proportional allocation, each stratum is represented according to its size. In proportional allocation, each stratum variance of y bar of st is given by the variance of y bar of st with the proportion value, proportional allocation. So since we have already the formula, so uh, here we can see that proofs also. 1 by n square summation I runs from 1 to k of ni into ni minus ni of s square divided by ni. Here we are replacing that value with the p. So p value can be replaced with ni divided by capital Ni. This will become 1 by ni divided by n square. The second step, ni of divided by ni minus 1 of s square. If you do the cross multiplication, you will get the same. So why we are writing here, it is ni divided by n value will be the pi value. So 1 divided by n is a constant, n minus 1 divided by n of s square. We are removing I values with the general notation. So 1 divided by n of minus 1 divided by n of summation I runs from 1 to k pi into s square. So next, coming to the proportional allocation. After that, then name and optimum allocation. Optimum allocation is the principle in the determination of ni's to choose them. First condition, minimize the variance of the estimate with the fixed sample size n and fixed cost. Minimize the total cost for fixed desired precision. In this optimum allocation, ni's are to be obtained such that variance of y bar of st is minimum for fixed sample size and variance of y bar of st is minimum for fixed cost. Cost also it is fixed. The total cost c is minimum for fixed value of variance of y bar of st. Let's see some theorems. These are the conditions which we so far discussed. Next, excuse me. Variance of y bar of st is minimum for fixed total of size of n. That is what we have to prove here if ni is directly proportional to the ni si. Hence the problem is to minimize variance of y bar of st. Formula we have 1 by n square summation I runs from 1 to k ni of ni minus ni of s square divided by ni. Subject to the condition summation ni is equals to n, it is fixed. This is equivalent to the minimizing. So what is a minimization function? Just consider phi of variance of y bar of st with some constant summation lambda summation I runs from 1 ni minus n. Okay, we have to minimize for this partially differentiating with respect to the ni. Okay, unconditionally for the variations in ni and lambda is unknown large sample. For a minimization, phi is we have to differentiating with respect to the ni and equating to 0. So partial differentiation if you do only for ni, so what will be here? So if you keep on multiplying that values to the both, then and also there is no term of the ni value, summation ni values you can say and put it in equating to 0. So in first step, the differentiation value at 1 divided by n, that is 1 divided by minus 1 divided by n square, ni si square of n square will be the constant plus, and there is no term in the small ni, so this will become 0 plus lambda of summation ni is be the 1, summation 1 value will be the lambda. Okay, and there is no ni, so this will be lambda. So lambda will equals to the negative value will become the positive. From this ni you have to derive ni NISI divided by n into 1 root of lambda. Put it as equation by taking summation on both sides with we have I runs from 1 to k. So I runs from 1 to k ni summation divided by NISI of n of root lambda. So summation ni will become the capital small n. So n equals to so from this you have to derive the value of root lambda. Substitute that root lambda from a and b. Ni is equals to NISI of done n divided by summation NISI divided by n into n. So here small ni is always directly proportional to the NISI. Hence the theorem is proved. By substituting ni value of the variance of y bar of st, so we will get the equation and the formula. Okay, let's see now. Putting ni value is n into NISI divided by summation NISI. So variance of optimum allocation, we will get the value. So wherever small n is there, you have to substitute that. After substituting and getting cancelled some values, then you will see on simplification, that is 1 divided by n of summation I runs from 1 to k pi si square minus 1 divided by n of summation I runs from 1 to k pi si square. Here is the whole square, here is individual square. Next, the cost function. Let's see some cost function in optimality. Very important. What is a cost function? Let A is observed that the cost function in the sample survey, and CP is denoted by a cost per unit in the ith stratum. Then the total cost C is given by the linear model. C is equals to A plus summation I runs from 1 to n Ci into Ni. Now in stratified random sampling with the given that the cost function of C is equals to A plus summation I runs from 1 to n Ci Ni, variance of y bar of st is minimum if Ni is directly proportional to NISI divided by root of Ci. For this proof, here we have to minimize the variance of y bar of st subject to the condition C is equals to A plus summation I runs from 1 to n of Ci, which is fixed. It is equivalent to minimize phi function variance of y bar of st plus lambda of summation I equals to 1 to k Ci Ni plus A minus C. Okay, so here unconditionally for the variations in small ni and lambda being Lagrange's multiplication differentiating or partial differentiation formula with respect to the ni and equating to 0, then we will get dou by dou ni of phi is equating to 0. If you see the each term, then the 1 by n square will be the constant, and n square minus of n square of s square divided by ni is constant, and if we are multiplying for each term 1 by n square, next lambda of will be the same. If you do partial differentiating with respect to and equating to 0, then you will get NISI square minus of divided by n into n square Ni square plus C I into lambda. Okay, here the C is the extra term. Okay, so here the value is equating to right hand side of Ni square, then it will become NISI divided by n into root lambda of root C. Put as equation 1. Now taking summation on both sides over I equals to 1 to k, then this will become summation NISI under root of Ci of Ni of n of root lambda. We have to consider the find out the value of root lambda, then summation I runs from 1 to Ni of, that is NISI of root lambda root lambda is equals to n into small n. Put it as equation B. From A and B, substitute small ni value over there, then you will get ni n into ni of si under root of ci and summation nisi divided by under root of ci. This is in the form of the allocation for fixed cost. Ni is directly proportional to the nisi under root of ci. So thus the large samples would be required for a stratum. If the stratum size is large, the stratum variability is large, so sampling cost per unit is also low in the stratum. So in next theorems we are going to put it out the comparisons, and we will learn, we are going to finish it in systematic also. Okay, thank you.